Okay, hello everyone. Good to see you online. Hope everyone is doing well. I'm gonna start sharing my first slide deck. Okay, I have no visibility. I have a, first of all, can you hear me? I'm not muted or anything. Should not be muted.
Yeah, we can hear you.
Okay, cool.
Yes.
So welcome to the 22nd San Diego Meetup. I have no, I don't have window of the chat. So if you have any question throughout this couple hours, feel free to stop me. It is intended to be um, kind of interactive. So yeah, just stop me, and if you have any question, please feel free to uh, uh, chime in and let me know what you want to talk about. Um, so this is the first slide that I show every meeting the past almost couple of years. Um, is there any new members? Anyone new here? First time?
Yes.
named
Hi.
Michael and Austin.
Good.
Yeah.
Cool. Good to see you. Thank you for joining. So the way I structure the meeting is usually it has kind of two halves. One is kind of a general topics that I'm collecting throughout the past month, and all kinds of interesting things in C++ and in software in general. I am always on the lookup for new uh, speakers and people that can, and it can, and again, I'm saying it every time, so I'm gonna say it again. Any topic, it can be varying from 5 minutes all the way to an hour or more. It's your choice. I'll be start being more aggressive in begging for people to have to participate in speaking during the meetup. Again, we are all here to learn and just getting more and more familiar with the language. Um, there are multiple levels of the language, and I'm trying to kind of fit everyone into a couple hours. So it's going to be beginners, going to be some intermediate, and maybe here and there some expert. But I am shooting for beginners and intermediate because I feel like this is the majority of the people they actually want to, and I definitely understand that they want to have more knowledge of the common and basic stuff, and gradually we can ramp it up into more into the intermediate. Um, I can tell for myself, I'm in the past month plus I'm learning Rust, and it is difficult. And I am, if I need to choose between different levels of the language, I'll definitely want to hear more about the basic stuff to get familiar with the basic things. Um, so the agenda, and again, please stop me if you have any question. The agenda today would be the following. We'll talk about the repo of the month. ASIO Networking library is what I picked, and I'll tell you why. We'll have about 10 plus minutes of lightning talk about big O notation. This is from kind of recommended by Jason Turner, one of his tweets where he recommended that this is from the Denver C++ Meetup channel. We'll talk about algorithms. This is one of my favorite parts, and what I usually do every month, I pick, and it's kind of random. I pick something that I've seen, like a question that might be in lead code or somewhere in Twitter, anything, and I develop something that can be a good platform for discussions about algorithms. And we had a lot of examples throughout the last couple of years that I'm running this meetup. And if you notice, in the past few months, I'm kind of trickling more and more about ranges. So we talked about ranges v3 and stud ranges, which is part of C++ 20. So we'll see more about ranges today. It's a very interesting addition to the language and very powerful one. And C++ 23 would have more coming that I'm aware of. So the ASIO networking, the Lightning talk, I would say would be, so the ASIO networking would be kind of an intermediate level. The big O notation would be beginners to intermediate. The ranges would be, it would be a bit of beginners, intermediate, and the ranges would be a bit of the expert part. But I'll go slow, and please ask me questions. I'm not guaranteed to know everything, but ask me question, maybe I can help. The C++ Stack Overflow question of the month. Again, I cherry pick something that I'm seeing on Twitter, my Twitter feed. Kind of a beginner, but it's kind of an interesting syntax that I'm never used, and I thought it would be nice to kind of present that. C++ quiz, I cherry picked 3 questions. They are from kind of beginners, intermediate, and there's at least one question which is kind of more on the expert part, and we can talk about it if you have any question. C++ High Performance second edition. It's a very new book that published, I think, a week ago. I had the opportunities. So this is from Packet Pub Publishing. They approached me and wanted me to review it a couple of months ago, and I reviewed the draft and send them feedback and all. So the reason I could actually recommend that is because I had a couple months of the draft. The book itself is on its way to my home, but I do have the draft that I reviewed, so I can definitely recommend. I really like the book. By the way, the first edition is also really good, but it's the first one goes all the way to C++ 17. The second edition goes all the way to 20. Very interesting book, and lots of things that you can learn. It's a very thick book, by the way, at least according to the draft. And the kind of the main course of the meetup this time would be the part 2 of the badge of honor, the C++ 11, 14, and 17 features, which are cherry picked for you. I don't know if I would have time to go over everything. I'll ask you at the end if this is something that you would like me to complete. If yes, I'll do another round. Okay, let me see if there's any questions. No. Okay. Okay, this is sponsored by Qualcomm Wireless R&D Software, which I'm part of. They sponsoring the meetup and paying the fees, which I thank them a lot. We have a Dropbox link, and we have a Slack channel, which I think is not very active. I think these days Discord, at least this is what I hear from my kids, Discord is the place where you wanna be if there is a request from anyone that we need a Discord channel. I don't mind to have yet another channel to maintain. Just let me know. We do have a YouTube channel that I upload my my recording, and I do it. I do it when my kids play, and it's I kill the internet for 10 minutes, and they'll shout at me. But that's life. Okay. We do have a Twitter account which I manage. My Twitter account is Kobe_CA. You can follow me. I tweet on software engineering, C++, C, Linux, Unix, Bash languages. Yes, including Perl if there is a Perl interesting article, C++, Rust, CMake, and so on and so forth. I try to avoid politics. So I'm trying to keep it very clean on software engineering only. Politics is for some maybe other media and social network, not Twitter. Okay, some changes coming up. I have a conflict actually. If you remember, we tend to have this meeting taking place on the second Tuesday of the month, and sometimes I screw up and I accidentally change it. It's not intentional, by the way. Usually, I have a conflict on the second Tuesday of the month, unfortunately, and I'm going to make it on the third Tuesday of the month. Hopefully, it's not gonna make a lot of difference from you all. Hopefully, I'm also shifting that, if that's okay, 1 hour early. So instead of 6 to 8, 5 to 7, I think 6 to 8 might be a bit late. The 8 part is gonna, in terms of dinner and all. So hopefully this is okay. If not, feel free to chime in, either send me a message or anything and tell me that no, it's going to be tough to do 5 to 7. Okay, let me see if there's any questions. No questions. Okay. Okay, so the GitHub repo of the month, I picked ASIO Networking Library, and the reason I picked that was because I was listening to the CPP cast episode about the networking TS, the technical specification. So C++, ASIO C++ committee, they sometimes release technical specification where people can take and try out. So there is a networking specification, technical specification that I think you can try out, or at least there is the draft that you can read. And maybe I should give you the link. So this would be the ASIO one. 1 second, I'll do this. 1 second. Just going to. Okay, I'm sharing my entire desktop. So you should see that. So so this is the ASIO, but what I wanted to show you is the CPP cast. So which I highly recommend if you have a chance, if you're walking your dog or anything like this. CPP cast is a great resource to learn about C++. So it varies between like 45 to 1 hour each episode. I think I'm gonna have a maybe next time an overview on all the podcasts that I'm recommending. There are a few of them. Actually, there are a few of them that are really new that just came out, which I'm very happy to kind of have the opportunity to listen to them. So during this networking TS episode, they talked a lot about ASIO library, and let me show you. So this Think Async is a great resource about the ASIO library. There is one which is the boost one, and one which is the non-boost. During the episode, they're talking about the uh, uh, the boost beast HTTP library, which is a very common library today to use for HTTP, and my understanding, it does use some flavor of ASIO, if I remember correctly. So basically ASIO, it's async IO, which can give you a portable way to do async operation on sockets and files and so on and so forth, which I recommend to check if you have this requirement to have a very robust and efficient efficient I/O. So it's very optimized and all. And I gonna ask you to go back and listen to this episode. There's a lot of information that you would be able to use if you happen to go and utilize this library. Yeah, so boost.org Beast. I remember in CPPCon 2016 that I participated in Bellevue in Seattle. I remember the author of Beast trying to convince people in like it would catch you in the corridor, give you like a flyer, yeah, hey, use Beast, and he managed to push very hard and get it accepted into Boost, and it is using Boost ASIO, which is kind of a flavor of this ASIO library. Okay. So do you see my presenter view, or you see only the? I think you see the presenter view because I'm sharing my entire. So let me just share. Okay. Do you see the slides again?
Yes.
Okay, perfect. Okay, lightning talk. This is going to be a 10 minutes of very interesting. I really like this subject about what is the big O notation and how do we take this into practice, right? So this is part of the North Denver Metro CPP Meetup channel. And so what I'm going to do, let me make sure that I including the audio. Okay. So you should be able to hear. If not, let me know.
Yes, I claim that big O notation is a lie, and if that sounds like clickbait, yeah, it probably is. But you guys can tell me at the end whether it's valid or not. So, okay, we all know what big O is at a group like this. We all know what big O means. Wasn't invented by Knuth, but popularized by him as the way to characterize algorithm performance. And so, from a practical point of view, this is how you talk about how your algorithm performs for large N. And so it's usually the primary guiding principle for choosing algorithms when you're worried about performance. And my point is that this can lead you very much astray. The three ways I'm going to show you are all things that I hit working at another company back in the 2000s before we had YouTube and you could watch Chandler Carruth explaining all this stuff at a CPP conference. I learned all this the hard way. So the first way that big O can be a lie is that there are special cases, right? So if we consider a sorting algorithm, right? Bubble sort is everyone's favorite bad way to sort things, right? Like don't do that, right? We all know it's order n squared, whereas standard sort is a good sort algorithm, and that's n log n, right? Right. One of the first big results in theoretical computer science is that n log n is the lower bound on sorting, right? So standard sort does that, great. But here's the thing. What if the range is already sorted? And you might think that that's kind of a silly thing. If it's already sorted, why are you sorting it? But you don't always know. Maybe it was processed by some other thing before it got to you, and it might be sorted. Here's the thing. Depending on how you write your bubble sort, if your range of stuff is already sorted, bubble sort runs in order n, right? Because it just goes through it once and says, oh, look, it's sorted, I'm done, right? So you get a big improvement in bubble sort in this particular case, whereas standard sort is still, at this point, comparatively slow. Or what if you have one element out of place, right? You've taken the last element and rotated the whole thing so that it's first, right? Again, depending on how you write your bubble sort, this is still order n, whereas standard sort is still going to be an n log n operation. So the point is that many algorithms have special best or worst case situations, but it's order n or n squared or whatever it is usually just the average case or the typical case. You may be very surprised to find out that you're in one of these special cases. So when you select your algorithm, read the fine print. Now, the second example, the second way that things can go awry is that you have to define what big means. And we didn't plan this, but this is almost exactly the same kind of thing that Jacob was talking about. We're going to make all pairs of something. But this is the first stage in a multi-stage thing. We're solving a problem that is fundamentally combinatorial, right? The thing you have to do is basically n factorial. And so you go to great lengths to haul that all the way down to something as good as like n to the sixth or something. And this is kind of the first stage in that. So what you've got is two sets of things. Each set is, so you got set A, set B. They each have n objects, and you want to find all pairs according to some multiple criteria, which could be very complex. So this could be things like you want all pairs that are that are physically close in space, or they have the same color, or they have similar signal to noise ratios or something. And some of these could be very simple. Some are very computationally expensive. And the criteria you're going to apply and the order that you apply them in is either specified in a configuration fail, or sometimes you will adapt at runtime and change them. So the implementation that we had at the time was to use standard.
Wait, someone said that you don't see the screen. Is this true? You don't see the screen.
You are sharing only PPT. So
sharing only the PPT. Okay, so you missed. So you missed all the. Okay, so let me just share the entire. Okay, sorry about it. I didn't realize. Okay, now you can see it.
Yeah.
Sets, and we all now, you grit your teeth. Oh my God, it's going to be slow. Yeah, it was slow, but this honestly worked for like a decade or something, right? So the idea is you take set B and you sort it in multiple ways, one for each criteria. So you end up with multiple sets, one for each criteria. And so for a given element A, you can sort of look up in one of those sorted sets of B, like where it would be, and then, or you might do like a lower bound and an upper bound to find all the ones that have the same value. Or if you want nearest neighbors, you would find where A would be in B, and then you traverse, you iterate forward and backwards in that sorted set to find the ones that are in some sense close. So I mean, this is a very complicated thing, right? It's kind of the high level view. And so when you get to the end of this, you get something that's very heavy in standard set operations, and it's something like n plus m times log n. Now, m is something like the number of matches you get from each criterion. And what you want is for m to be small, right? That means that your criterion filters out a lot of things you don't want. Or put it the other way, the value of m that you actually get from one of these tells you how hard your problem is, how hard it is to eliminate possibilities. Now, for the real problem that we were solving at the time, n equals 50 was considered hard. 300 was typically impossible, except unless the problem was very simple. Like you could do 300 if m is always coming out, 1 or 2 or something. I tried to feed it a problem size of a couple of thousand once, and we couldn't even set the problem up before we ran the Beowulf cluster out of memory, right? So it was a challenging situation. But after a while, we finally did, first of all, figure out that standard set is slow, but we came up with a very clever way of reformulating this, which I'm still proud of. I don't work at the company anymore. It's their intellectual property, so I won't describe it in detail, and I don't remember it anyway. But the idea is to represent everything in terms of boost dynamic bit sets. So instead of having like a standard set sorted in accordance to one of these criteria, what you would do is arrange for some number of dynamic bit sets, and then an on or off bit represents one object in B, and you arrange for your dynamic bit sets to have bits on or off that represent, say, closely grouped chunks of B. or something like that. So you would bin objects from set B into groups. You arrange for a dynamic bit set of each group. So for an element in A, you find the set of dynamic bit sets that match the criteria you want. You bitwise OR those together, and then across all your criteria, you bitwise AND them together to do a sort intersect. This was a detailed, complicated bit of business, but it pretty much gave you exactly the same results as the other thing and was way faster, like way, way, way faster. As in, what before would chew up 40% of your runtime is now 5% of your runtime. And the things you were worried about profiling, or that your profiler was telling you should optimize, simply disappear. The compiler optimizes them out; they're gone. Right? This was very successful, but then things got interesting because the mathematicians at the company looked at this and they called, well, politely they called horse bucky. Right? They said, "Wait a minute, I don't buy it. There's something else going on. There's something wrong here. I don't buy this." And the reason why is that the dynamic bit set, doing a bitwise AND or a bitwise OR to put all these together, that's order n. It's order n over 64 because dynamic bit set stores all of your bits in unsigned longs, right? But still, you've got maybe n divided by 64 of these to do as you iterate through and bitwise operate on them. So it's still order n. And for various complicated reasons, you end up having something like n of these dynamic bit sets. So the result ought to be something more or less kind of like an order n squared thing, as compared to an n log n, which is what we had before with the standard set approach. So the point being is that me and my coworker were claiming that an order n squared operation is way, 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 way faster than an n log n operation. The mathematician said, "I don't buy it." So we spent a bunch of time. We ran a bunch of simulations and came up with a bunch of scenarios. And we found that the point at which n squared was as slow, the dynamic bit set n squared variant was as slow as the standard set approach, which is n log n, was something like, I think it was about 700,000. It had enough digits in it that you had to mentally count over and put the commas in, right? In a problem where 300 is considered large, okay? So we said, wait a minute, what's up? Why is n squared, why is this n squared operation so much faster? And the answer, of course, this is what you've all been waiting for, is cache hits. These are numbers I stole from Chandler Carruth's talk from 4 or 5 years back at CPPCon. The point is that an L1 cache reference is something like half a nanosecond, whereas going out to main memory is, say, 100 nanoseconds. So it's 2 orders of magnitude. Standard set is node-based. We all know this. So every time you do anything to it, you're taking a trip out to main memory. So its order, let's put the constant in, 100 n log n. Technically, there might be 100 inside the log n, but never mind. This is good enough. Whereas dynamic bit set is a contiguous array of 64-bit integers. So every time you do anything to it, it's an L1 cache reference. So it's 0.5 nanoseconds. And you do n over 64 of them. So there's a 0.5 over 64 out in front of that. So if you actually plot that, you'll find that your n squared operation is faster than n log n for everything less than, say, what, 150,000? Okay, and here's the point, right? Big O notation tells you about what the asymptotic behavior of your algorithm is for large n. But how large is large? In this particular case, large is bigger than 150,000, and we're way the heck down here, where 200 or 300 is something we can't really handle. So the point is that in this case, big O is meaningless because that only means something if you're talking about an asymptotic behavior. So the point being is that what big really means is determined by all those constants that everyone usually wants to ignore, okay? And if your n isn't actually big, then which algorithm is going to be faster can be very surprising because your big O notation is basically lying to you about what it's really going to do. Big O is meaningless unless n is big, and you might not know what big means. You might have to go measure. All right. Now, the third thing where big O notation can trip you up is that there's an assumption that small means easy, right? We only worry about big N. We only worry about the performance of our algorithms for big data sets because of the assumption that if N is small, it's going to run fast anyway and you don't care, right? If you're only sorting 20 things, who cares whether it's fast or slow? On a modern computer, you won't notice, okay? So consider a problem statement, which is a follow-on to that previous thing, right? All those pairs that we were trying to make the number of pairs as small as possible, those end up feeding into hypotheses. So a hypothesis is a set of observations. Observations in real life may or may not arrive in time order because you've got multiple sensors and there's like network delay or something. But the operations you're going to carry out on these hypotheses require time-ordered data. So you have to keep these hypotheses sorted as new stuff comes in, right? So how are you going to do that? How are you going to keep your data sorted as these things come in and you keep adding them? Well, our original implementation was, again, standard set, because back in the early 2000s, that's what you used for these. And okay, fine, we learned that standard set is slow, and so we went to, say, a standard vector plus a standard sort, because that's what you do to sort stuff. But of course, what we found is that, okay, you might think that for n equals 20, and that was typically the biggest size that a hypothesis would be. Look, it doesn't matter what you do, it's fast, and this is actually true. It doesn't matter what you do until you got 200 million of these things to handle. And 200 million hypotheses was not a difficult problem, okay? I mean, or rather to say it's difficult, but this was typical, right? And if you got that many 20 element things to sort, the behavior for, or your performance for n equals 20 becomes really important. So the point is that while standard set insert is, you've already got a standard set and you're going to add one, that's ordered log n, right? That's going to be fast. But consider that a standard vector you push back and you call a standard sort, well, it's order 1 amortized for the pushback, and then it's n log n for the sort or something. But of course, it's in a standard vector, so it's going to be much faster. We found that out. But remember, we talked about earlier, I mean, bubble sort is usually slow, but bubble sort can be order n if it's already sorted except for one guy that's out of order and he's always on the end and you bubble sort the right way. So you go to a standard vector with a pushback and a bubble sort. And now when you're doing order 1 plus order n for a billion hypotheses, this makes a huge difference in runtime. Although even if it was this, it's actually a fact that bubble sort is faster for small things than standard sort is. That n squared, yeah, is totally swamped by the fact that the algorithm is so fast and so simple, and the compiler can optimize it, right? And everything's local. So the point is, and of course, what you really do is you just start doing a linear search from the back to find out where your new guy goes, and you put him in because he's almost always going to be near one end of this thing. So you do this and you optimize for a small case, which ordinarily you wouldn't worry about. And again, we got huge speedups, like factor of 2 or something. All right. And so when you're doing 100 million or a billion of these, the n in your algorithm isn't the important thing. It's how many times you have to run it. And in that case, standard wisdom for what what the big O behavior of your algorithm is, again, totally irrelevant. All right, because the fast ones are the ones that big O notation would say you shouldn't even look at. So the point is that big O notation is a lie. Now, it's not a malicious lie. It's a lie we tell to children, right? Because the universe is complicated. And it's still a good first guess. I mean, you don't know which algorithm to use the one that looks fastest, right? Just keep in mind that this can be deeply misleading because you've got special cases. The constants out in front matter, aka really what that really comes down to is cache locality. Cache locality typically swamps all other considerations. And even behavior on small cases matters when you've got a large number of small things to do. So I claim that big O notation is a lie sometimes. Thank you.
Okay, so the takeaway would be you would definitely need to think about theory and practice. They need to meet. And it kind of reminds me, I don't know if you remember, but I had a presentation on the parallel algorithms, and we concluded that we need a very big numbers to show benefit of the parallel algorithm, at least in the use cases that I showed, which were use cases that are taken from all kinds of books that I mentioned back then. Okay, let's continue. Okay, that's one of the fun part of the meetup. It's gonna start with kind of basic, beginners to intermediate, and we'll end up with a more of the expert part of this section. So a few weeks ago, maybe 3 weeks ago, I bumped into a tweet, and I had this screen capture of the tweet, and the tweet is here, so you can see it. You have the slides, and you can take a look at that. And someone, this lady was asking, like, anybody knows how to make stud vector of pair int, like a pair of ints, and to basically flatten it. And she was like, I want to have this number pair, which is a vector of these pairs. So the way, again, for the beginners here, the way you can initialize, it's like vector looks like an aggregate. So you have this external curly braces, and then each pair is this kind of a tuple of this 1, 4, 2, 3, and 3, 9. So we have 3 of them, right? Very simple. So there is a vector of this stud pair. And basically pair is you can think about it like a struct of these 2 integers. It's very simple. It's a struct of 2 integers, and vector is a class which has a dynamically allocated space on the heap, and maybe a couple more. I don't remember the exact layout, but some bookkeeping of what's the capacity and what's the size, and I think that's about it, if I'm not mistaken, maybe roughly on the ballpark. And people started, and I'm here. You can see me here. People start kind of like, what exactly you want, and how can we help you? And she was like, I want to take this number pair and pipe it into ranges view. And if this is the first time you're looking at ranges, by the way, you can see my screen, right? You can see this slide. Just make sure that
we see the picture.
you see the picture. Solving algorithm, right?
Yes.
Okay, perfect. Okay. So so if it's the first time you bump into this syntax, if you work on any shell, Linux or Unix shell, and you take an app and you pipe, so you take the app and the output is piped as an input to another app, which is the output is piped to another app as an input, and so on and so forth. You chain it. So this is the idea. What C++ is capable of is to overload this operator. Basically, a pipe is an operator, and you can say, okay, I'm overloading this operator to have a specific the syntax have a specific semantic and like a specific functionality. Without going into details about overloading, if you have any questions, I can definitely maybe present something sometime in the future about overloading. But for now, just think about this. This pipe means number pair, which is a vector, is piped into something, and eventually we take these numbers that were like the result of all this expression. We iterate and we print the numbers. And what she wanted is to take some hierarchy. So we have a pair of inside a vector.
Sorry, Kobe. I think we are on the wrong screen.
You are on
We
the
are
wrong
just stuck with the picture, the taken from the Twitter thread discussion. Is that what you're
Yeah,
sharing?
yeah, this is the one. Yeah.
Okay, so you're moving your mouse in middle only, right? The blank part.
Yeah, I'm let me so can you see my
Okay.
pointer?
Yes, now we see the pointer on the.
Okay. So solving algorithm. So
Yeah.
so basically you have this loop which takes these numbers, which is behaves like an iterator, and we print one number at a time. But she didn't know how to do that, and I found it a very interesting thing to solve, and I tried all kinds of stuff. I show you what I tried in this few slide deck that I'm gonna present, but all the code is on my public GitHub. Okay, so initially what I thought she wanted, and you can look at the thread. If you take 1, 4, 2, 3, and 3, 9, eventually you want to have 1, 2, 3. So 1, 2, 3, and then 4, 3, 9. So 4, 3, and 9. So let's take a look how we can do that. And we'll start slow. And please stop me if you have any question about the syntax, because the purpose here is to learn new things. Using plain loop. So this is the next slide. So plain loop is very simple. Eventually, what we want to do is we want to print all the elements, right? So this is C++11 for loop. It's a range for loop. So we have this out, which is the vector of integers, and we populate the vector with the values. Okay, so so each value would be here e, and we print it. So clog is from IOStream, and this is the for loop that actually takes the number pair that I showed in the previous slide, and for each pair we push these two integers one by one. So the way it's being done here, which is that I think that one of the simplest things I could think of, because I wanted to show you all kinds of like evolution of things. So this number of pair behaves like an iterator. So you take one pair at a time, and there is a C++17 structure binding, which I really like. This is one of the features in C++17. There's a lot of good features, but this is a good feature which gives us a very efficient way to extract let's say the pair in this example into distinct values, instead of having that first or that second. If you happen to work with pairs, there's that second, that first and that second, which is not very informative. I can have a key value here, and if you coming from Python or Rust or maybe other languages, this is a very modern way to do that, right? And eventually, when I take the key value, I push back k, I push back v, so I'll have the key values flattened into a single vector, and I can print it, and I'll have 1, 4, 2, 3, 3, 9. So basically, it would be 1, 4, 2, 3, 3, 9. Okay. So that's one way. Please ask questions if you have any. The second one is actually she proposed that in one of her tweets in this thread. She said, okay, this is what I have. And let's see what she was proposing, because this is a very good example to learn about other approaches and algorithms. Okay, so we have the same deal. We have this out. I'm kind of removing the part of where I print the elements, but it's the same as this print. Once you have the vector, you can print it. So I'm kind of removing that to make it a shorter slide. So I have two expressions here. So I have this output vector that I'm gonna iterate and print. I have two expressions here. One is a lambda. I'll explain what is a lambda in a second. And then I have an algorithm. You can ignore this static cast void. This is a good practice if you want to say, hey, I'm kind of ignoring the return value from transform. Some coding standards require that you explicitly say that you don't care about the return value, but just ignore the static cast for a second and just concentrate on these two expressions here, and I'll explain what it is. A lambda, it's basically a syntactic sugar for a callable object. Now, it's very powerful and all, but just for the sake of this discussion, think about it just as a function. This is the function parameter, and auto means it's like a template. It is a template, but just bear with me if it's new. If you're new to Lambda, just think about it that P can be any type. Okay, and these curly braces are the body of the function. So this is just a function. Okay, so it's a function. I can take it and I can pass something to this function, and this out vector would do pushback on P dot first and P dot second. So when the compiler compiles this whole thing, it requires that P, which it can be anything, but it needs to have a dot first and dot second. If it doesn't have it, there's going to be an error. So this is kind of an assumption that we have that compile time would enforce. Okay, this is a way. This brackets is the way to capture out by reference. If you're coming from C, think about it like I'm passing a pointer and then dereferencing it, and then at the end, after I'm using this function, I'll have an out that is populated with P dot first and P dot second. Now, it's really clunky, I know, but that's one way to do it. Okay, so there is this stud transform. C++ comes with a lot of algorithms. The library is full of more than 100 algorithms, and it's growing, and they have multiple overloads. So you can do the math. That's a lot of algorithms, and they have also flavors of parallel algorithms where you can run the algorithm in parallel. Like the standard library would do it for you. For example, I think GCC, I think lib standard C++ has TBB underneath, if I'm not mistaken. But the bottom line is that stud transform is one of them, and stud transform is very simple. What it does is the following: you provide this algorithm a range. So from the first to the end of the number pair, and again, number pair is this guy. It's a vector of pairs. So I have 3 pairs in this case. So I'm saying I'm gonna iterate from the beginning of this range to the end of this range. So this is the syntax: stud begin and stud end. Yes, you can do also number pair dot begin and number pair dot end. It's the same thing, and it's the same exact same performance. This is, by the way, very this begin and end in vector is really cheap. Okay, so because vector is just an array. It's a dynamically allocated array, so the begin and end is just pointers. The iterators are abstracted as pointers, or basically they are pointers. Okay, so the idea is that we have a begin and we have an end, and then I have the third parameter to this function tells what do I do when I take one item from the range. I'm passing it to a specific function. The output of this function would be pushed into, in this case, out. So again, I'm iterating through this via this range. For each element, there is a for loop here. Transform is a for loop. For each element in the range, I'm calling a function. The function would do something, but it would also return me a return value. I take the return value, and in this case, I push it into the vector. So back inserter, doesn't matter how it's implemented. Just think about the fact that it just take the result of a function and do pushback on this vector. So this vector would have pushback for each result of this function. So what actually
performance-wise, is this any better than the looping approach?
Not really. This is actually even much cleaner, but this was also presented, and since it was part of the thread, if you were reading it and bumping into that, I wanted to explain what it does.
Sure.
But in my opinion, this is very cumbersome. I'm not suggesting you to do this, but it's a good point just to have a discussion, because if you see such thing, my opinion is if you have the opportunity to refactor that, I'll refactor that as a roll loop, because this is much cleaner. And if you wanna this is doing pushback. If you wanna have performance in mind, I would even, if you know the size of number pair, I would pre-allocate out. So there's a lot of things you can do, but this is much better than this one.
Makes sense.
Okay, so eventually what happens here is for each element, there is a for loop internally. For each element, we call this add function. Remember, this add is a syntactic sugar for a function. This is the body of the function. So what happened here, for each element, which is a pair, we do push back on the vector, and then we on the first, and then we return the second. So you have two pushbacks, one of the first and one of the second. Essentially, you'll end up with this. But it's just obfuscated, in my opinion. So I'm not suggesting that, but this is something that you might see. I'm actually suggesting that you fall back to this. If you have a choice between these two, just fall back to this. But the requirements from this person was to use ranges v3 specifically with the pipe syntax. So let's see what can we do. So the first thing I was thinking, if you look at the thread, is, hey, use join. And because I know that join works in some cases when you want to. So join is basically a very good way to flatten a vector. So you have a vector which has some hierarchy. So ranges can do this join. And there, by the way, you have this compiler explorer link. You can play with it in compiler explorer if you want to when you have the slides. So that sounds good. We'll have this 1 4 2 3 3 9 and it's gonna be fine. But unfortunately, I was wrong. It didn't work. And that actually was kind of confusing, because I know that join works at least with vectors of vectors. So what's the big deal? Why stud pair doesn't have the same capability of having stud vector of vectors? So this is, if you go and put it into
so you're saying that if it were not a pair but just a vector of vectors, the syntax works?
Yeah. This is my next slide. Yeah.
Okay.
Because what I did, I started with something that I'm familiar with, and start playing with it and see how stud pair is different from vectors. So this is what happened when I tried to have stud.
Does it expect some kind of homogeneity in the types of the?
I think it expects some a specific iterator which pair doesn't have.
I see.
So that was the issue, in my opinion. And if you read the very long, you can see the scroll. This is just a capture of the first I don't know, 10% of the error. It just there's a lot of things, and it just didn't work. But again, I remember seeing that, and I have a slide on where I was remembering seeing that, and I have a reference of ranges. So I started with stud vector, and so okay, is that going to work? So what happened here is that I take this number pair, and I pipe it into something that gives me view of everything, and then I do join. This is an action. Basically, in a nutshell, there are two main things that you can do with ranges. One is a view, which is a lazy evaluation, very cheap lazy evaluation, and then there is an action, which actually mutate it. It's going to have some mutation happening. And this number pair pipe to view of all, and then I have a view of all, and then join would give me some iterator kind of ranges. I could make it a vector, but I didn't want to do it in this example because I didn't need to. What I needed is some iterator that I can iterate and print it. But I could pipe it into something that makes it a vector, and you'll see an example soon. The auto here is type inference, super important in this case. The type here of auto is very, very long. So auto really helps us in C++, in modern C++, which is C++ 11 and above, to basically have a sane syntax and not like a very long kind of type that is really cumbersome to type. So that works. You can go to the C link and you'll see that I have 1, 4, 2, 3, 3, 9. Okay. So how can we solve it with going back to stud pair? So I was thinking about it, and I looked at the options that are available in ranges v3, and I came up with one solution, which I didn't know if it's a good or bad, but it's a solution that works. So what I did is the following. So this is stud vector of vector, but this is again the stud vector of pairs. So I have the same stud vector pairs, and what I did is the following. Forget about the ranges views concat right now. Take the number of pair and pipe it into keys. So I discovered that there is something called keys that I'm actually giving any pair or tuple that has two values. For example, stud map has a stud pair inside, right? A map has, you map a key to a value, right? So giving the number of pair, I can extract the keys, given, and then there is a comma here. So this is one parameter that I'm passing to concat. And the second parameter, giving the number pair, I piping it into value. So basically what I did here is that now I have a lazy evaluation. I have two views, one that would give me all the keys if I traverse it, and one that gives me all the values if I traverse it. Nothing really happens here. Only when concat, and concat basically takes two views, right? Only when concat start traversing, this is where things actually happens. So it would take all the keys and then all the values and concat them into one range, and then I can iterate to them. And what I'm getting is 1, 2, and 3. You see here, and then 4, 3, and 9. And that actually surprisingly worked well. But I wasn't sure that that's what she needed, because that was my first approach, and I had keys and values, but I told myself, hey, wait a sec, what if she needs 1, 4, 2, 3, 3, 9? Because what I did, I took all the keys, and then I took all the values, and then concat them. But what if she needs a real flatten, like not keys and then values, but key value, key value, key value? Basically, what I've been doing here, key value, key value, key value, right? So I was thinking, okay, what else can I do? And I came up with this approach. Okay.
I have just one question.
Sure.
So the header file, so if I want to run this program on my compiler, so to get that header file, where should I look up to for that range _/v3 _ all.hpp?
Are you talking about this header
Yeah.
in Compiler Explorer?
Yeah, I mean, the standard online compiler says no, I mean, compilation failed because of this header file.
Okay, let me show you. Okay, let me show you. It's a good question.
Yeah, I'm using this one. The compiler that I use is also suggested by you, the cpp.insights.io.
Okay, so let me do this. Let me share. Okay, so let me. You can see my screen, right?
Yeah.
Okay. So Compiler Explorer, by the way, is a very amazing tool online. Has this libraries tab. Okay,
Oh.
so when you they kind of overhaul it, but I have ranges v3 selected because I have the bookmark of this. But if you go all the way, you can see all the things that are supported. And ranges is already picked, so you're not going to see it. But if I want to have example boost, so I can add boost. Okay, so ranges would be here. So I picked 0.11, and then once you pick it, then this ranges v3 headers would be available to you.
Oh, okay.
Okay.
Yeah. Thanks.
You're welcome. Yeah, thank you for the question. So let me go back here. Is there any questions so far? Let's go next. Okay, so the next one was, okay, can I do a real flatten? That's what I wanted instead of doing keys and then values. So here's another approach which is very similar to what I don't know, similar, but using ranges, views, transform. Okay, so here's the deal. Remember that vector of vector walked, right? So this was my idea. Okay, if vector of vector is walking, can I take number pair, transform it into vector of vectors, and then use join, and then I'm done? Because vector of vectors join works, right? I can flatten vectors of vectors, but I cannot flatten vector of pairs. So then the idea came as, okay, let me try. So I looked up and I said, okay, there is a transform. So for each pair, I'm creating a vector. So what happened is that eventually I'll have a series of vectors. Each of them has the key and value, first and second, right? Because P basically is the pair. So for each number pair, for each element, which is P, I'll get the first and the second. I'm creating a vector and returning that. And then I pipe it into join. And I'm done. Basically, kind of I'm cheating in the way that like I'm actually transforming that to something that is joinable. And then I print it. And then it gave me a real pure flatten, which is 1,4,2,3,3,9. Okay. And then she was coming back, like the original author of this thread, and said, "Look, I actually need a unique. I like, it's not enough to have it flattened. I actually don't want this 3,3 to repeat. I don't want it to be repeated." It's, oh, you want you want unique values only. So that was another thing that yeah, it killed my entire night at the same that day. By the way, like I went through all this exercise, but I said, okay, if you need a unique values only, let me go back to my concat solution and do the following. I'll do concat of number pair, getting keys and values. So the concat ends here. So from here all the way to here. So what I have here is 1, 2, 3, 4, 3, 9, because I concatenated keys and the values. Then I pipe it into an action that creates a vector. So I'm creating a vector of this whole thing, sorting it and making unique. So this is an action, this is an action, this is also something that is actionable. And then I ended up with 1, 2, 3, 4, and 9. And basically this is the solution that she needed. And she took this solution, integrated, and told me that everything was passing in terms of unit test. I was, of course, super happy that I could help. But I learned a lot of things by doing all of these things, all of this exercise, and hopefully I managed to kind of get things also passed to you. I just want to call out on my helper booklet for Ranges v3 that I purchased. This is actually, I think, shipped from Europe. You can buy the PDF or the printed one. I highly recommend the printed one. I don't think it's super cheap. I think it's a bit of like 30, 40 bucks. But amazing reference for Ranges v3. This is the first edition. I bet this person, which I don't know who's behind this Wallet Fox, but the nice part of Wallet Fox is that they're doing a lot of very nice illustrations. Okay. I have a couple slides, or maybe one slide on Conan, how to build, if you want to build Ranges v3 on your desktop, not using Compiler Explorer. I have the recipe how to do that. And take a look also on the notes of the slide, of this specific slide. There's more explanation how to use Conan to bring it into your. I use Conan to bring. I'm not like building Ranges v3 from source. No, I'm not doing all of that. I'm using Conan, and within a couple minutes, I have everything I want. What I like in Conan, it's like a virtual environment for that Python provides. It's pretty nice. So use it if you need. Okay, and I couldn't pass Rust because I learning Rust in the past couple months. Not an expert by all means, of course. As just a beginner, but here's one of here's a solution. Not sure if the best one, but the solution that I could come up with. So number pair is a vector of tuple, which pairs in Rust, creating an iterator from this vector. And then there is this flat map where you take this, for each element, I call it top tuple, and I create a 2 elements chained, which are also behaves like an iterator. And this is not a Rust meetup, so I'm not gonna go over this once and all, but you can go online and take a look at the Rust documentation. Then I do dot sorted. I'm sorting the whole thing, making it an iterator unique, and creating a vector, and then I can print it. So this flatten is a vector, and I can print it. This dot collect is very similar to this to vector. So you can see that it's very similar in terms of the sort and unique and all of that. I took the same approach. So the Rust part is also kind of very clean. Okay. Stack Overflow of the month. What is this syntax? Like, I never used class boot star. Boot is what being used, but apparently this is like in one shot you can have, and I have the link for the Stack Overflow, by the way. it's a syntax. First time seeing that, by the way, where you can have in one line you can have a for declaration of boot and then use it here. So instead of doing class boot and boot star boot and the prototype, you can have just in one line, which I found a very interesting approach. Okay, 3 quizzes. So let's do it. And what I think I'm going to do is just going to share my entire desktop just to make it easier. Okay. So this is an expert question. I'll explain very shortly what does it mean here. So you have a stud string of x. Okay, this is a C++ 17. Its difficulty would be 2, which I think is 2-3 in my opinion. So stud async would take 2 parameters. One is what is the async policy, which is async. There's few policy to async, and then a function. And what is async is doing, it's going to asynchronously run this function. Remember this lambda, it's quote synthetic sugar of function. And what we do, we pass x as a reference. You can think about it as a pointer. We dereference it and assign y. And then we immediately go and do the same, but we run a function asynchronously, running a function that does x equal z. And then we print x. And the question is, what is the program guaranteed to output, or maybe compilation error, or maybe undefined or unspecified or implementation defined? So what's happening here? And since we are kind of, it's 7:15, I'm still on this part, I'll kind of gonna explain what happens here. So stud async, in general, it's an async operation, right? It would take this function and maybe run it on a thread that the standard library is spawning for you, and then we run this on another thread that is spawned, and then there might be a race condition because both of them are accessing x at the same time. It's very bad. You either want to serialize it or not. So the answer might be we don't know, or it's undefined behavior, or it's very bad because there is a race condition, there is no critical section, and so on and so forth. But here is this like a small gotcha that I really think that you just need to remember that. I don't have any way to kind of enforce this knowledge, because I just remembered that async returns something that calls future. And again, it's kind of on the very kind of expert level. Future, it comes from like say other languages. There's other like modern languages. They have this element of channels between. If I have, let's say, 2 threads, I can have a channel between them, and they can communicate via this channel. And there is this future is an object that can have that can receive a result from a different, let's say, a producer thread can create a result and send it over this channel to another thread that holds a future, and the future would provide information about is the producer done? Can I consume the result, and so on and so forth. So stud async returns this future, but if you're not picking this future, so there is no return value here in this example, right? What happened here is this would block until the function is done. And then this would again block until this function is done. So eventually, what happened here is that these 2 async are not really asynchronous. They're not really parallel. They're actually happening synchronously. And I have a very good article from Scott Myers. You know Scott Myers, right? Everyone knows Scott Myers. He's one of the biggest persons in the. He retired from C++, but Remember this effective C++, more effective C++, all these books, he's the author. So he has a very good kind of short explanation about what happened. So you see this std async gets a future. The thing that you need to remember, it's a gotcha, is that async, if you don't consume the future, it's gonna be blocking. And then this whole thing is synchronized. So what happens? You'll have Z, and there is an explanation what happens here. So this is an expert. If you're ever using async, this is a huge gotcha. Just make sure that you're aware of that. Okay, let's do something a bit more simple. So according to C++ 17, you have a character pointer string. This is, if you are coming from C, there is nothing special here. And then I'm having std cout of this string. Is this okay? And std cout is basically like, if you're coming from C, it's like a printf, but it has like a more modern way to do it, where you don't need to do this %s or %d or all of this stuff that might be undefined if you're making mistakes. So there is an issue here. This is not going to compile. And the reason for that is this must be const. According to C++ 17, this must be constant. There is explanation about what happens. And so just remember that a C++ 17 compliant compiler would not let you compile that. This actually makes a lot of sense, because this would be on the read-only segment, and you really don't want to change it. Actually, I had opportunity to play with these kinds of code in the past, where I actually went and changed that, and very bad things happened. Like the program actually crashed. Like modern compilers would crash it. Like the code that is generated would crash it. Okay. So remember to have a const char pointer to make it. Okay, this is interesting. It's a bit more on the intermediate and expert, but bear with me for a second. So we have a template function, and the template function is really a function that gets any type. And this is a syntax of C++ 17. Actually, it's actually from 11, not only 17. Actually, this variable argument to templates is not 17, it's 11. So here's the idea. So I have a function sum, and I pass 1, 2, 3, 4 numbers. Some of them are double, some of them are integers. And again, I have a sum. Again, some of them are double and some are not. So what is the value here? So the secret behind that, which you need to understand, and this is whole deals with numeric promotion, which comes from C, by the way. The idea actually behind this question is how C works. It's not really a question on C++. Beside the syntax, which is a pure C++, but this question is more about how C++ inherited numeric promotion rules from C. Okay, so let's take a look what happens. So I have this sum, and the first argument has a type of t, and then the rest. So what it's doing, it's taking the argument plus, again, it's a recursive function. It takes sum of t and the rest of the argument. So it's going to do argument plus an argument plus an argument all the way until this is the, if you know how recursion works, this is the function that would stop the recursion. So there is the last element and just return the arg. So we'll have arg plus arg plus arg. So we basically sum all of them. But what happened here is the first type here is a double. The first type here is an integer. So let's see what happens when we take sum and we take the first argument here, and then we say, okay, I want sum of t. So sum of t in this case T, if you think about it, the first type here is double. So I'm taking 0.5 plus sum of double of the rest. So I'm enforcing everything from that point on to be double. So what happened here is that we'll have 0.5 plus 1 plus 0.5 plus 1. So it's 1 plus 2 plus, so 1 plus 1 plus 1. So it's 3. So let's see what happened here. So here, basically, actually, I said promotion. I meant casting. Sorry about that. So the second part would be I'm taking 1 and sum of t. So what is t? T is the type is integer. So I'm actually forcing everything from that point on to be an integer. So it's going to be casted. So I'm doing 1 plus an integer of 0.5 would be 0 plus 1, that's 2, plus, again, 0.5, and I'm forcing everything to be an integer. So it's going to be 0. So it's basically 1 plus 0 plus 1 plus 0, which is 2. And this is how it's, so there's this explanation happens here. You can take a look at that if you're not convinced. Hopefully my explanation kind of makes sense. Okay, book recommendation. I mentioned that C++ second edition. I highly recommend if you have if you want to pick one of the latest books on C++ high performance. It talks about micro benchmarking. It talks about C++ 20 ranges and coroutines and lazy generators and everything that you can think of. It talks about the differences between different containers and which one is more efficient than the other one. Again, going back to this big O notation. A very good book, in my opinion, to read. This screenshot is before it actually was released, but it's actually released. I took it a long time. It was eventually released in Jan 2021, so it's already released. You can pick it up in either PacketPub or in Amazon. By the way, I just remember that PacketPub might give me few few coupons for the ebook. So if I have one, have few of them, I'll post it on the Meetup webpage, and you can grab it. I don't know how much they'll give me, but I don't know if first come, first serve kind of a thing. Okay, the last slide before we go into the other my main course, which it's already 7:30. So there is something that that we call in C++, actually it comes from 11, which is in Scott Myers. I just mentioned him in Effective Modern C++. Actually, his last book that was talking about 11 and 14, and then he retired from C++, from teaching C++. There is this forwarding references and what we call also universal references. That forwarding references is the official name. So forwarding references can be done either with auto-ref-ref, and this is, by the way, kind of an expert topic. So if you kind of feeling lost, don't worry. We can talk about it in length in different. But if you're familiar with this, you should understand that a forwarding reference is either auto or T in a template. Anything that you add either to the auto or the T would not make it a forwarding reference. And the idea behind a forwarding reference is it can accept an R value or L value, can accept everything. So this is a very powerful type that can accept a temporary or a literal or anything and work with it. So you can see that this is not a this is not a forwarding reference. This is basically an R value reference. An R value reference is a reference to an R value, to maybe a temporary or maybe a literal, something that we can take the address of, okay? And here someone put const, and this is immediately, compared to this is not a forwarding reference. This is a const of an R value reference. So when you pass either R value reference, 4 is just an integral, or if you pass an L value, so it's an L value because it's on the left side of the equation, right? You can take the address, it's an L value, would compile on both of them when you pass F. But here, an L value does not compile because this can only accept an R value reference. You cannot pass an L value. So this is something, and by the way, this is from WalletFox. This website has a lot of other slides that you can learn all the features, not all, but a lot of features in C++, in modern C++. Okay. The next one is really, the next deck is really targeting beginners, maybe to intermediate. So hopefully things would be a bit more sane. I know that the last slide might be a bit on the expert side. So kind of repeating myself from last time, I was working on this slide deck since August because a coworker was asking me, "Hey, Kobe, I did a lot of C++ in the past, but many years I'm not using C++. I'm not really working with modern C++, and I don't really know what's out there." And that actually gave me an idea to do a very simple presentation on all the modern C++ features that you can really, in one slide, you can hopefully understand what it can do and start picking it up. Of course, each slide is really simple. It's not intended to be exhaustive, but at least it gives you a way to pick it up and work with it. And what I did, for each feature, I assigned a badge. Is it portable? Does it provide you speed? Does it provide you maintainability? Is it safe? Is it more readable? And so on and so forth. And we went through a lot of, not a lot, but maybe 12 slides. And I have a slide that I created that what we went through so far. And I'll post the slides online, and this is the slides are really self-explanatory, so you should be able to, even if you're not familiar with that, you should be able to take it and use it as a reference for modern C++. So we went through all these topics, and I'll continue today with the other topics. So we talked about no except, strongly typed enum, initializing list, range-based for loop, which you saw in my previous slides. Null pointer, so use null pointer, don't use null, don't use 0 to denote a null pointer. Auto, this is C++ is not a dynamic language, but type inference, just like Rust has type inference, it's really nice to have. Final class, override, explicit constructors, const member function, and using declaration. Okay, so C++ 11 added syntax to say, hey, I want the compiler to generate this function for me. So what does it mean? So take a look at this class, or maybe a struct. By the way, class and struct interchangeably used here because class is basically everything here is public, is private, and struct everything is public, the default access specifier. So if I have a constructor, and a constructor, if you're coming from C, a constructor is basically a function that I can pass parameter and it gives me back a class. or a struct. So I can construct a class or a struct by passing this parameter. And other languages, they have something very similar. Rust has something similar, not exactly like this, but something similar. And the idea behind that in this example is that when I create my own constructor, I'm losing the default constructor. The default constructor is very handy sometimes if you just want to create a class of foo and you don't want to pass any parameter, you just want a class foo. So the rules in C++ are if you create your own constructor, the default is gone. But what if you want it? So before C++ 11, we needed to kind of create our own constructor, like empty constructors, and say, okay, I want this empty constructor. So the compiler have it. This new syntax that says equal default provide me this opportunity to tell the compiler, look, I actually want this constructor, so bring it up and have it available for me. In this example, I want to have a virtual function, a virtual destructor in this class. So let's say I want a base class, and virtual destructors are very important for a base class. I'm not explaining here why, but just if it's new, if you're new to this, just remember this rule. The rule is that virtual destructor is needed on the most part for base classes that are intended to be used as part of a polymorphism system. So I can tell the compiler, hey, I don't want to create my own empty virtual destructor. Just generate one for me. So this equal default is very handy. It's really good for mutability. You don't need to create your own empty functions, but you tell the compiler, hey, just generate this for me. You know best how to do it. And by the way, the compiler knows the best how to generate functions. So let the compiler generate the functions for you. The flip side is, hey, I want to delete function. And like the compiler usually has a set of special function that it's going to generate for me. But what if I don't want the compiler to generate? And one of the things that sometimes you don't want the compiler to generate is copy. So if you're coming from C, there is no such thing as functions that are used to copy struct to another struct instance. There is no such thing, right? Copying of struct are bitwise copy. There is no special function that takes an instance and create another instance from the old instance. Copy constructor or copy assignments, they are here to help us to actually to create this functionality. But what if I don't want my class to be copyable? And there are many reasons that you don't want your class to be copyable. You just want to disable copy, so that you can still pass this class as a pointer or as a reference, just like in C, but you can make copies of this class. And if you think about it, sometimes you have a class that has a handle, and it doesn't make sense to make a copy of this class and have another handle, right? Because it doesn't make sense semantically speaking that you have two instances that they have handle that points to the same resource, right? If you think about it, there are multiple reasons not to do that. So before C++ 11, we needed to do all kinds of ugly tricks to remove that capability, but now we have a very good way to do it. We just do equal delete, and we delete it. This is actually very handy if you want to delete anything, any functions, any overloads, anything that you think that you don't want the compiler to have visibility to. You can do equal delete. So it's very important for safety. For example, if let's say you have a very expensive class or a struct, and you say, okay, maybe someone is making a mistake. Maybe someone is making a copy of this class. This is bad. We don't want to make a copy. What you do, you write these two expressions. You delete the capability of making this class or struct being copyable, and you recompile your code. And the compiler would tell you, hey, you are making a copy here, and you catch it and you fix it. Maybe pass a pointer or maybe pass a reference. So it's a very, very handy feature that I use very frequent and a lot, actually. Okay, we have a lot of algorithms that we're being added to the standard. There is a very nice thread here that someone, this person is the author of std format that is replacing printf and actually an IOStream and providing us. This is part of C++20, by the way, std format, and provide us a much better performance compared to any other formatting tools. Sorry. So the funny part is, take a look at the size of the algorithms header. And by the way, the algorithm header is not the only algorithm. There's not the only header that is being used for algorithm. There is also numeric and maybe others that I can remember. But take a look at algorithm. Take a look at how it's expanding from 10 to almost 20 in SPAS 11 and 14. 11 and 14 are basically kind of the same. 14 is a bug fix of 11, and then almost 40. So 10, almost 20, almost 40, and 62. This is pretty impressive. C++20 has ranges. This includes the parallel algorithm. Be familiar with that. See, the CPP reference here has a lot of information. There's a lot of good, if you need any good either books or tutorials online and CPPCon and so on and so forth, recording, let me know. I'll post it. You can search for 101 algorithm CPPCon talk. It's a 1 hour, 101 algorithms, a great one that would give you an overview of all the algorithms in 1 hour. Okay, Lambda. Lambda is one of the most powerful things that we have in C++ 11 and above. And the reason for that is it creates a lot of opportunities for if you use it correctly. It's more readable than having some function call, maybe a pointer to a function. It's heavily used as part of algorithm. Remember this std transform that I mentioned? This is a very handy way to pass a function to algorithms. Let's say you have an algorithm that want to do something for each element. So this is you pass a function. How do you do that? You pass lambda, and this is not new in the software industry. The functional programming languages, there is Python, there is Rust, there is Haskell, there is Java, JavaScript, anything on earth, Kotlin, anything on earth has something that is a lambda, and basically just a callable object. It's just a function, but it has a weird syntax, but it's just basically a function. And it's really I'm so amazed by when looking at the generated code. If you go to Compiler Explorer and look at the generated code is really optimized. Like, it's really zero cost abstractions. The compilers, the compilers today, like the latest compilers, are really good at optimizing it. That is pretty impressive. Jason Turner, by the way, in this C++ weekly YouTube channel, has a good number of recording that he had on Lambda. There are many books, Lambda stories and all. If you want me to recommend you on books, just ping me and I have more than you can chew. I think there's lots of them out there which are really good. Okay, variant. Variant is basically a safer union. So if you're coming from C and you know what a union is, stud variant is a let's say a safer approach than using the C union. So if you look at this variant, you can have an integer, you can have a float, you can have a string. If you have a state machine, you can have states, and these states, these stats can change the state as you want, just like in union. But it removes all the undefined behavior that we have with union, and it adds all kinds of functionality to the variant. You can take a variant and make a function call on it, and it would do the right thing. So I found it very useful. We use it a lot in our code base whenever we need a union-like functionality. So stud variant is really, really handy. I believe lib authors would find it very, very useful. It's really easier to maintain than union. It's much safer. Union has all kinds of gotchas that you need to be aware of. Much more readable than union, and there's some kind of on the expert side of using stud variant where you can have a very nice productivity and usability, which I'm not showing here. But if you're interested in, there's a lot of good blogs and also books that you can look at. Very powerful C++ 17 feature, by the way. Another C++ 17 that I heavily use is optional, and I'm super happy that C++ 17 had it, because if you look at the modern languages and modern computing and modern semantic, optional is everywhere. And optional is basically a way for us to have a semantic of I have something or I have nothing. And if you're coming from C, you tell me, oh, Kobe, I use -1 for I don't have that. And this is what the standard library is using, right? The libc is using let's say 0 for success, or maybe something lower than 0 might be failure, and maybe the number might be an error. No. The problem with that is that sometimes I need the entire range of the value in order. Even -1 is a valid number. So let's say everything is a valid number. So what do you do? Do you create your own magic number that denotes a failure from this function? How do you communicate that? And how do you create a syntax when you read your code? How do you make it easier not to make mistakes? So optional, again, it's not a C++ invention. It's something that was there in many other languages, even Java, JavaScript, Rust, and other languages. They have it. So so obviously C++ 17 also added that. The nice thing about optional is that you can use it as a Boolean. You say, if is there any value here? If yes, I can do something. And if there is a value, I can dereference it, which makes the reference is basically an overloaded. But there is also the .get that you can have, okay, .get, or there's lots of functionality that I encourage you to look at. It also helps if I want to do lazy initialization, like I want to initialize something, but I don't know yet how to do that, and I don't want to use pointers and do allocation. I want to have it a non-pointer. So how do you do that? Lazy initialization is done by stud optional. I think one of the very important additions to C++ 17, it makes your code, once you start using it, it makes your code much more readable. And since it's a template and all, the compiler is doing a very good job in optimizing all the functions that the reference and all to a very good machine code. Lib authors would use it. It's much better in terms of readability than the -1 and all of this stuff. It's much safer. The code looks easier to read and to write because you have either something or you have nothing, and this nothing is forced if you do if. So please use it instead of I don't know, -1 or anything like this. Of course, if get foo is a boolean, it returns a boolean, this is enough. If it's a true or false, this is enough. But if you have a number, but you want to denote, look, I don't have it, so you need a syntax for that, and C++ 17 provides this syntax. Okay, forget about macros. Don't use macros unless you have a very specific. So macros are really good if you want to have like a repeatable, like you want to have some syntax that is repeatable. But for everything that is defining a specific constant, macros are really bad because macros, they don't know anything about the language. It's a search and replace mechanism that happens before the actual tokenizing basically happens, right? First you do search and replace, right? You do the preprocessor, and then because you can do -E on GCC and you can see the preprocessor output, and only then you start doing all the tokenizing. So it can give you all kinds of funky if you happen to have a pound define something that someone else is using and you're just replacing this token with another one. It drives you crazy. And in my career, I had a lot of time when I needed to do -E to understand, hey, why is this funny compiler error? Like, I'm not doing anything special, and I just to realize that someone did a pound define of some macro, and I just happened to either include a file or maybe use something that used the same token. It's being replaced, and now it doesn't make sense for the compiler, and the compiler is like, give me some varies. So don't use it. Use const expr instead. It is a compile time, so this whole thing would be a compile time, so you don't lose any efficiency. It's the other way around, and the standard is actually going into direction where everything that can be const expr in terms of support, it provides you support of const expr, like constructors and so on and so forth. So Jason Turner has a lot of const expr recording, which I recommend to watch. You can see the power of that. You can do a lot of compile time computing and all just by using const expr. So compile time, there is no runtime here, right? Okay, Chrono. So Chrono is one of my favorite C++ 11 addition. The reason for that is that Chrono allows me to do all the, just have a syntax of time and duration in a safe way, and more important, I'm not losing any performance. The important part of Chrono is that when you have 100 millisecond, it has a type. It has, you can't accidentally take 100 millisecond of an integer. Like before you had Chrono, you had 100 millisecond of an integer and 100 nanosecond an integer, and you do plus of these two integers, and you do the wrong thing because you didn't scale one of them to the right domain of the other integer, right? So by using Chrono, if you take a millisecond and you take a nanosecond types and you do plus, in compile time, and this is the important part, in compile time they are being scaled, and then in runtime it's just doing the plus. super important. Like, there is no reason to start using integers for anything that is a time related. There is no performance penalty. So if you're using C++ 11 and above, you should use chrono for anything that is a time related syntax. In C++ 20, we getting additions of calendar, time zone, and other things that I'm very excited to have. It's pretty nice. You can have weeks. You can have, like, you don't need to do any special computations. Everything is provided to you, and leap years and all of that is taken care of. Very nice. I gave Chrono, I think, every single badge that I could have because it's really important library in my opinion. It's by the way, the author did an amazing job. I think it's one of the best designed libraries in the C++ standard, in my opinion, and probably other opinions as well. Okay, variadic templates. You already saw that in this quiz that I mentioned, where you have, if you remember, there was this sum function. The idea is that in compile time, so remember in C you have this ellipsis, which is basically a runtime thing. Here it's this ellipsis is a compile time. So I can have a compile time number of arguments, or if I have a class, I have a compile time number of types. It's kind of on the expert part. So it's really, if you're really into metaprogramming and you're a lib author that you have your own library and you need to have a flexibility, then you might use it. This is not something that you would use a lot on your daily job, but good to know that there is something like this. Tuple, for example, is something that can can hold a collection. Okay, so my collection here internally has three types. So if you do size of my collection, it would have int plus float plus string. The first element, so it's like a struct. So it's a struct that has an integer, float, and string. So if you look at it, it's a template. But I can have a tuple of int, I can have a tuple of int and float, I can have a tuple of int, float, and string. So how can I achieve that? This is achieved using variadic templates. So the author of tuple is doing that. This is a very useful, again, this is a modern, it's a C++ 17, it's a modern feature from other languages like Python and Rust and JavaScript, probably Java. The nice thing is that take a look at this syntax. This is a pure C++ 17 syntax. I have, and this is, by the way, the runtime cost is nothing here. There's nothing. This is all done internally. I have a collection of integer, float, and string. I can make a collection of these three types, and I can extract them. A, B, and C in this case would be 3, 3.0, and a string Kobe. So tuple is being used a lot in a lot of applications to get a heterogeneous collections, and it's basically a struct. This my collection is, if you look at the layout, it's just a struct of three elements, but it's something that you cannot achieve in C because the syntax doesn't allow you. Yeah, the end result would give you just like a C struct. There is no overhead, but you cannot. There is no syntax in C that tells you, hey, I want to create in one line. I want to create a struct that has an integer, float, or string. There is no such thing unless you have a macro. Okay. Decal type. Decal type is a way for me to say the following. Look, I have an auto I equals 0. So 0 is an integer. Auto, in compile time, auto would be integer. And then I can say, okay, I want to have an X that has the same type of I. So I have a decal type of I as the type, and then X is the parameter or variable equal 3. This is nice because if tomorrow I put 0.0, I would be a double and X would be a type of a double because I'm tying these two things to be the same. It's really nice for maintainability, by the way. And I can do crazy stuff like I have a function that returns a double. So this is a simple function. If you're coming from C, there's nothing C++ here. But I can say, okay, I don't care what the function is returned. So this function, I'm calling this function. Like this is in compile time, the compiler would say, oh, what is the return type of this function? Oh, it's double. So decal type of this would give me double D 3.0. So these all kinds of tricks, very useful in maintainability. If it's the syntax looks new to you, think about the opportunities that you can have. Very, very useful if you need to use types that are connected to each other. C++ 11 gave us a lot of types and semantic and syntax that is related to multithreading, locking, mutex, and so on and so forth. Mutex is new in C++ 11. Before C++ 11, we needed to do whatever C was doing, right? If you're on a POSIX environment, you'll do you'll run pthread or POSIX related function or API. If you're on Windows, you need a Win API. So here we have a standard way to have a mutex. We have a standard way to have a threading, and lock guard is one of this whole thing where I can acquire the mutex here, and the mutex is released at the end of the scope. The idea that there is something happening in C++ when you are done with the scope is what we call RAII, is one of the most powerful things in C++. And I just I'm rereading a book named Pragmatic Programmer, the 20th edition, and apparently Ruby code has the same idea where you are done with a specific scope, you execute something. And what happened here is that lock guard has a destructor. So when you end a scope, there is a function named a destructor that is C++ from day one. And this destructor is doing mutex release. So you don't need to deal with, so all the resource allocation and deallocation is handled very nicely. Versus in things like C, you need to do something like go to some label of cleanup, and it's really messy, or you forget to do that. The idea of using this type of syntax is super powerful. I think one of the most powerful things in C++ in general. Okay, it's 8 p.m. This is a hard stop. I have a question. I have other things. I'm basically 27 slides out of 50. Is this useful? It's really on the beginner side, but is this something that you would like to see me completing this whole thing? I'm okay if yes.
It's very useful.
It is useful. Okay.
It's more of a refresher, even for intermediate developers like myself. Just refreshing our knowledge on things that we might have forgotten.
Yeah, I agree. That's actually the whole point of this. So I'm going to continue next time, and I think what would happen next time is I'm going to shrink the first part so I can actually complete the 25-ish slides next time in Feb, and because I agree it's a very good refresher to. That's the whole point. That you can definitely in one slide deck you can have all the things that are very important for you to know, and then you can go back and just research that yourself in more depth, like in more details. Okay. Is there any question?
Yeah, I was going to ask, do you have a link to the Big O notation is a lie lightning talk?
Yeah, I do. I'm going to upload the slides in a day or two, maybe tonight, and I'll post it in the meetups. The slides are uploaded, and there is a link there.
Okay, thanks.
There's a link to the session and link to the channel as well, the Denver channel that is.
Okay.
Okay, thank you for sticking to the end. Hopefully you had fun. I know I did. See you next time.
Thank you very much, Bobby.
Thanks, Kobe.
Thank you.
Thank you.
Thanks.
Thank you.
Thank you.
Thank you, Colin.